Okay, in this recording, what we're going to do is I'm going to record both section 6.2 and 6.3 together, since 6.3 isn't very long. Um, so we're going to be calculating milliequivalents and, of course, calculating your units in this one. So we're going to still be using a lot of the ratio proportion methods as well. So although most medications are dosed using the metric system, milligrams or grams, some medications will be calculated using other units of measure, and some examples of those substances are salts, proteins, insulins, penicillin, and um, heparin. So many fluids, of course, contain dissolved mineral salts and electrolytes are conduct a charge through the solution when they are connected to electrodes. So measured by milliequivalents, which are related to molecular weight. So um, the atomic weight, I gave you a review of some terms, is the weight of a single atom of an element compared to the weight of a single atom of hydrogen. Molecular weight is the sum of the atomic weights of all atoms in one molecule of a compound. A millimole is a molecular weight expressed in milligrams. Milliequivalent is the ratio of the weight of a molecule to its valence used to measure the concentration of electrolytes in some volume of solution, also an amount of medication that will provide the patient with a specific amount of an electrolyte. Valence is the ability of a molecule to bond as indicated by its positive or negative charge, and represented by a superscript plus or minus sign next to the element symbol. So those are some definitions of some words you may hear through this chapter. Milliequivalent equals the molecular weight over the valence. So this shows you an example of what the valence looks like. The sodium ions is Na+, chloride ions is Cl negative, calcium ions are Ca++. So, but most commonly, plus or minus is going to be like 1, 2, or 3 of them. So you might be asked to add, as a pharmacy technician, you may be asked to add 28 milliequivalents of sodium chloride to an IV bag. This would require calculating an amount of milliliters of sodium chloride solution to add to the IV bag, given an available solution, such as 4 milliequivalents per 1 milliliter. So calculations will involve determining the volume of course, it's of a substance, of course, that has electrolyte as its primary ingredient. So here's an example you have here. So again, we're just going to use ratio proportion. Here you need to add 44 milliequivalents of sodium chloride to an IV bag. Sodium chloride is available. It's 4 milliequivalent per 1 milliliter solution. How many milliliters will you add to the bag? So if you look here, you're going to use ratio proportion. You know you're trying to find X milliliters, so it goes right there, of 44 milliequivalents, and then it comes in 44 milliequivalents per 1 milliliter. Okay, so then you just cross multiply. So 4 times X always goes on the bottom. 44 times 1 is 44. 44 divided by 4 would equal 11 milliliters. So this chapter is pretty much just showing you different ways to calculate different solutions, but you're still using the same ratio and proportion method. Okay, in this question here, you have, of course, been instructed to add 15 milliliters of sodium chloride to a patient's IV bag. Using the label shown, calculate how many milliequivalents of sodium chloride will be in 15 milliliters. Okay, so if we look here, we know we have the X milliequivalent in 15 milliliters. Okay, then you're going to look on your label, and that's where you're going to get your 4 milliequivalents per milliliter. So we have it written here for you already. X times 1 would be 1. Always goes on the bottom because you multiplied it by X. 4 times 15 is 15 times 4 would be 60. 60 divided by 1 would be 60 milliequivalents. So a few more definitions. Of course, we're going to be calculating units. It could be insulin is read in units. Heparin is another injectable read in units. corticotropin, factor 8, penicillin sometimes can be, and vitamins. So these are some things that in the pharmacy may be read in units. So a unit is the amount of activity associated with a medication that has a biological impact on a patient. And you do not abbreviate international units as IU or U because sometimes it can cause confusion and allow you to make mistakes. So usually you just write out the word units instead of putting the abbreviation. So insulin syringes are available in the following standard sizes. You have 30 unit, 50 unit, and of course 100 units. On this picture is showing you that 100 units equals 1 milliliter. This one is 50 units equals 0.5 milliliters, and notice how they're writing out units. 30 milliliters is equal to 0.25 milliliters. Okay, so just to give you a few examples using your ratio proportion. If you look at this label, of course, a patient is to receive a bolus concentrated dose of heparin. If the dose is 7,500 units and you have a vial with the label shown, so we have our stock bottle, it's 5,000 units per milliliter. How many milliliters will you prepare? So we know our X is going to be over 7,500. So if you look here, you have the X milliliters over your 7,500 units. And then on your stock bottle, it was 5,000 units per milliliter. So that's where we got this number from. Then you want to cross multiply. 5,000 times X is 5,000. 7,500 times 1 be 7,500. Divide that by 5,000 and it comes up to be 1.5 milliliters is the amount of milliliters you need to prepare it. This next picture here is what just to show you, but that with the insulins, things will vary just very, very small. Okay, so when reading the insulin labels, you must pretty much carefully read them because they have very little or very slight differences between them. So it is often something that can be misfilled because it does have those slight differences. So when filling a insulin medicine, my best suggestion is to always carefully double check the NDC numbers. Okay, so if you notice here, you have Humulin R here, you have Humulin R here, but your units up here are 100 units per milliliter. Over here, they're 500 units per milliliter. Okay, so you always want to check those NDC numbers to make sure that you have the correct one. Only insulin syringes, of course, should be used to administer or dispense insulin. Here is an example. Okay, a patient is to receive 32 units of regular insulin each morning before breakfast. Insulin comes in 100 units per milliliter, which it tells you in the wording, but if it did not have it on that, you would find that information right here on the bottle. How many X milliliters will the patient receive with each dose? So you're going to have two questions here. And then you're going to find out how many days the vial will last. Okay, so first you want to figure out how many milliliters the patient will receive for a dose. And you could do this several ways. I'll do one the way the book tells you to do it, and then there's one way you can kind of figure in your head a little bit. But just do whatever's easiest for you. But of course, part one, calculate the volume of the patient will receive with each dose by using either the ratio proportion or the dimensional analysis. I only like to use that dimensional analysis for converting. I use the ratio proportion for everything else. It's just easier for me to do it that way. So here's your ratio proportion. You have X milliliters in 32 units. That's where we get that. Then it comes in 100 units per milliliter. So then you're going to cross multiply. 32 times 1 goes on top. X times 100 goes on the bottom. 32 divided by 100 is 0.32 milliliters. So we have found our dose. Okay, so using the volume per dose, just calculate, determine the number of days a single vial will last. In this example, the patient takes a single dose a day. So one thing you want to know is we know, of course, the dose is 0.32 0.32 milliliters per one dose. Well, a patient can take a dose more than once a day. So, but we know up here it told us just each morning, so they're only taking it one time a day. Okay. So what you need to do is you could do this in ratio proportion, which they did. Okay, so you have, of course, the X number of days. Where they get the 10 milliliters from, so if you looked on that vial, that is the amount of total milliliters in that vial. So what they did is put X days divided by 10 milliliters, and at that you know that they're taking 0.32 milliliters in one day. So they made it a ratio proportion. Cross multiply, 10 times 1 is 10. X times 0.32 is 0.32 goes on the bottom. 10 divided by 0.32 would be 31.25 days, or 31 days. Okay. They put that portion in ratio proportion. Okay, where I was telling you could do is, to me, and this may be in years of just practicing in the pharmacy, you could set it up in the ratio proportion if you like. But if I know a patient's taking 0.32 milliliters a day, and they have a total of 10 milliliters, if you just divide the 10 milliliters by the 0.32 milliliters, it'll tell you the same thing, 31.25 days. Okay. So this is always usually the total, and this is per day. Okay, and then when you divide the total by the per day dose amount, it'll tell you how many days it'll last. Okay, so that's my little shortcut instead of resetting it up to 2 ratio proportions. How might a prescriber write 4 times a day or daily on a prescription? They can write it Q6H for every 6 hours, or QID 4 times a day. Because the every 6 hours, anytime you have that, you always think of 24 hours is in a day. So you take the 24 times it by divided by 6, and you get 4 times. Okay, next problem set questions out of 6.2. Okay, you have your X milliliters. You go look at your label here. And then if you go into your book, excuse me, let me go look, page 164, I'm sorry. This is number 10. On page 164. So look, if you read number 10, it says add 50 milliequivalents of potassium chloride to a patient's IV solution. So to find out what that is, you're trying to find X milliliters over 50 milliequivalents. And you're using the potassium. In the book, it asks you to determine which label you would use, but I've already put that on here for you. You could use the 10 milliequivalent, which means 2 milliequivalents per 1 milliliter. Okay, then you just cross multiply. X times 2 goes on the bottom. 50 times 1 is 50. 50 divided by 2 would be 25. So you do 25 milliliters of the 10 milliequivalent. Of the 50 milliequivalent, excuse me, using that particular bottle with the 10 milliequivalent. Okay, next here's another one, and this is referring to question number 9. And you're going to add 27 milliequivalent potassium chloride to the patient's IV. So you know by looking at the label you have 2 milliequivalents per 1 milliliter, and you're to add 27 milliequivalents. So you're trying to find X milliliters. So again, multiply X times 2. It goes on the bottom because you multiplied it by the X. 27 times 1 is 27. 27 divided by 2 would be 13.5 milliliters. So you would select the 30 milliequivalent bottle to get that information. Okay, here is another problem we have here. This is number 13 on page 165. The following order is received by the pharmacy using a vial with the label shown above, the sodium chloride. How many milliliters should you add to the bag? So you have the prescription is below it, and it says give 132 milliequivalent of sodium chloride in 100 milliliters, infused at 62 milliliters per hour. So we know we're trying to find X milliliters, and it's giving you a little bit more information than you need. But you just need the 132 milliequivalent, how much they're wanting to give. And then you look at your label, and it's 4 milliequivalent per 1 milliliter. Okay, cross multiply. You get 132 over 4. 132 divided by 4 is 33 milliliters. Again, here is one in units. This is number 15 on page 165. So if you read your number 15, it says a patient is to receive 4 units of oxytocin using the vial with the label shown above. How many milliliters will be needed? So we need X milliliters and 4 units. Look on the bottle. It has 10 units and 1 milliliter. So you just want to cross multiply, and that 4 times 1 is 4 goes on the top. Then you have your 10 on the bottom. 4 divided by 10 would be 0.4 milliliters. Okay. And we have some more examples there, but I think you kind of got the idea. They're pretty much all the same. Just be careful when you set it in the ratio proportion. Make sure the units are the same on the top and the units are the same on the bottom. And then always when you multiply, whatever you multiply the X by, always goes on the bottom of the second step. Okay. Okay, so now we're on 6.3. You're going to be using solution powders, and you're going to do the ratio proportion like you have been, and then you're just going to do a simple subtraction exercise. So in preparing solutions, the active ingredients is discussed in terms of weight, but it also occupies a certain amount of space. So this space is referred to as the powder volume. So powder volume is the space occupied by dry pharmaceuticals, calculated as the difference between the final volume and the volume of the diluting ingredient, or the diluent volume. The amount of space occupied by the freeze-dried medication in a sterile vial used for reconstitution. So your simple subtraction would be your final volume, what you get from your ratio proportion, and then you're just going to subtract your diluent volume that they give you, and that's going to equal your powder volume. And it's also abbreviated PV equals FV minus DV. So a dry powder antibiotic must be reconstituted for use. The label states that the dry powder occupies 0.5 milliliters. Using the formula for solving for powder volume, determine the diluent volume. You are given the final volume of 3 different examples below with the same powder. So it kind of gives you some examples there. Again, this tells you you can have the 2 milliliters minus the 0.5 equals 1.5. 5 milliliters minus 0.5 milliliters would be 4.5 milliliters of the DV. So here's an example. You are to reconstitute a 1 gram dry powder. The label states that you are to add 9.3. So that's your add. So I always circle that first because that's going to be your second step. Okay. Everything else you underline is for your ratio proportion. So you have 1 gram of dry powder. The label states you are to add, anything that says add, 9.3 is going to dilute it to make a final solution of 100 milligrams per milliliters. What is the powder volume? So if you come down here, you're going to calculate the ratio proportion. What they have done here is they go ahead and convert the gram to milligrams, but I like to set it up first. So you have 1 gram, trying to find X milliliters, and you know it comes in 100 milligrams per 1 milliliter. Okay, then I go in and I go, liquids are the same, weights are not. So 1 gram be the easiest, be 1,000 milligrams. Okay, so then you already have your conversion there, so it doesn't confuse you later. So that's what they have done here. They've already ahead and converted the 1 gram to milligrams. So they've cross multiplied. You get 1,000 divided by 100 would be 10 milliliters. Then you are to add 9.3 of diluent to make the final volume the 100 milligrams per milliliters. So all you need to do is subtract, even though it says add, you subtract the 9.3 from your 10 milliliters. Okay. So it'll show you that here in the next step. And you get the 0.7 milliliters. Okay, so I'll do a couple of examples with you. These are pretty self-explanatory, I think. If they're not, just email me and I can do some more examples and post them online. But on page 169, if you go to number 1, you need to make an injectable solution a final concentration of 375 milligrams per 1 milliliter. So I'm going to go ahead and add that on there. On the hand, you have a vial that contains 1.5 grams. And the instructions are to add 3.3, so we're going to save that for last. What is the powder volume? So you call it X milliliters. So again, you have milliliters the same on the bottom. On the top, you have two weights, but they're not the same. So we're going to convert your grams to milligrams, and you get 1,500. Then you cross multiply. 375 goes on the bottom because you multiply it by X, and then 1,500 times 1 is 1,500. Divide those two, and you come up with 4. Okay, so now we go back into our problem. It says to add 3.3 milliliters, so then you're going to actually subtract 3.3 to get the dV. And when you take 4 minus 3.3, it's going to equal 0.7 milliliters. Okay, next we have page 169, number 2. The pharmacy must add water to an oral suspension before it can be dispensed to the patient. The dose is to be 250 milligrams, which we have, in 1 teaspoon, okay, because it's a liquid. And the dry powder is 5 grams. So we will put milligrams as weight, so we're going to put that on here. Trying to find X milliliters. Always, usually with the powder volumes, you're going to find X milliliters. How much water must you add? Okay, so we notice here none of our units match, but we do have liquids on the bottom. Okay, so the easiest here is to take the 1 teaspoon, change it to milliliters. Say it's 5 milliliters. Up here you have milligrams, grams. It's easier to change the grams to milligrams. Okay, which would be 5,000 milligrams. We've converted it. Cross multiply. 5,000 times 5 would be 25,000. Divided by 250. Okay, you can take that out, simplify that 1 0 if you want to, but 25,000 divided by 250 or 2,500 divided by 25 is going to come out the same. It's going to be 100. Okay, and then you are to add the 8.6. So then you're just going to take 8.6 and subtract it, and you should come up with 91.4. And that is all I need to show you for 6.3. So, and I didn't do as many examples on this one because it's kind of repetitive. But if you have any questions or run into any problems, just send me an email. I'll be glad to work up some more problems and post them on Blackboard, or you can come by my office and I can show you as well.